In this episode, we're going to go over graphs and vectors, but in the episode that follows this, we are going to do many examples of graphs, and that's where you'll get a really solid understanding of this. As always, if you enjoy this content, like and subscribe. So let's start out where we have two vectors. A vector is something that tells us magnitude, in this case 3 meters, and direction, in this case north. So if someone goes for a walk and they walk 3 meters north, that's going to be the vector quantity of displacement. And if this person walks 4 meters to the east, then that's again going to be the magnitude and the direction east, and that's their displacement. So if they walk 3 meters north and 4 meters west, what's the result of that? Well, the result is what we call the resultant. And the resultant, because we have a 3, 4, 5 triple, that resultant is going to be 5 meters. But there's another way that we can look at this. Let's say that we draw our vectors in such a way that we align the tail to the tail. If we form a rectangle, the rectangle method, we can draw the resultant like this. If you think of it in terms of forces, if we pushed something north and we pushed something east, it would go northeast. What angle would that be? That would be our angle theta. Now you can think of this right here as the horizontal component of the resultant. So in other words, this goes both north and east. How much of this vector goes east? Well, that's going to be the adjacent side of the triangle. If we have the hypotenuse and the adjacent, then we can say that Rx is going to be equal to the resultant times cosine theta. And similarly, if we're looking for the northward component, how much of this goes north? That's going to be opposite over hypotenuse. So Ry would be equal to R sine theta. So what is the resultant? The resultant is the result of two vectors, or it could be 3 or 4, but generally in this level of physics we do 2 vectors. And the components are the portions of the vector that are acting perpendicular to that resultant, in this case east and north. So let's solve a simple problem. Let's say we have a boat that's crossing a river. The motor pushes the boat so that the boat travels at 3 meters per second across the river. But the river is flowing east at 4 meters per second. The question is, how far does the boat get displaced horizontally? In other words, what's going to happen? As the boat travels in this direction, it's also moving in this direction. So the boat's going to end up somewhere over here. Now, these are not displacements, so we can't just simply do a right angle vector diagram like we did before. So what we have to do is find out how long it takes for the boat to cross the river. So we can say that the average velocity is equal to the displacement over time. Well, how fast is it going? It's going 3 meters per second. And how far does it have to travel? It has to travel 24 meters. So what's the time it takes to travel? That's going to be 8 seconds. Well, now we know that it takes 8 seconds to cross the river. How far down the river is it going to travel? Well, again, the velocity is constant at 4 meters per second, and this time we know the time. It takes 8 seconds. So what's the horizontal displacement? 32 meters. Here's a tricky little question. What if we're given the resultant? So B is our resultant in this case, and A is our component. What other component, component C, would have to be acting on it so that B would be our resultant? Now these aren't at right angles to each other. So instead of drawing a rectangle, we draw a parallelogram. So I'm going to draw a parallelogram like this. And connecting these, we have our two parallel lines and two other parallel lines. Our resultant from C would have to be in this direction. Now, this should make sense because think of it in terms of forces. If these vectors were forces or pushes, if we pushed something up and to the right and we push something up and to the left, it's going to go somewhere in the middle of that, somewhere up. Maybe a little up and left or maybe a little bit up and right, but in general, it's going to go up. Let's take a look at projectiles. So if I have a soccer ball that's kicked at an angle and it follows this parabolic trajectory, what are the vectors going to look like as it travels through the air? So we're going to neglect air resistance. So air resistance is going to have basically no effect. And what happens to this kick? Well, we know that the ball is kicked up at an angle. So that's going to be our initial velocity. But what are the components of this velocity? Well, some of this up and right kick is acting in the horizontal direction. That's going to be V naught cos theta. And in the vertical direction, again, we have a rectangle here. That's going to be opposite and hypotenuse, so that's going to be V naught sine theta. And we can say, as the ball travels through the air, that its velocity is going to be changing because we have a force of gravity acting on it. Now, the direction of the force of gravity is down. And we know if this is the only force acting on it, it's a net force. If the net force is down, then the acceleration has to be down. So this is only acting in the y direction, meaning that it's only the vertical component that's going to be affected by this acceleration. There's no horizontal acceleration because there's no horizontal net forces. Nothing's pushing on the ball to the right or to the left. Now, initially when the ball was kicked, that was true, but we're looking at it only after the ball got kicked. I'm going to define up as positive and down as negative. So let's first take a look at this vertical component. The velocity is up and the acceleration is down. That means we're going to see it slow down. So the vertical component is going to decrease. When the vertical component gets to the top, it no longer has any vertical velocity. It's not moving up and it's not moving down. So our Vy has become 0. On the way down, we have an acceleration down acting on this, so it's going to speed it up. So it's going to gain y velocity. And because it continues to accelerate down, the acceleration is in the same direction as the velocity, it speeds up, and if it lands at the same height that it took off at, then the magnitude of this initial y velocity is going to be equal to the final y velocity over here. Now let's look at the x velocity. This is much simpler because there are no accelerations. If there's no accelerations, then the x velocity is going to remain the same. Now, if we take a look at what the resultant velocity is, the resultant velocity, we draw a rectangle, looks like that. This is sort of interesting because at the top, it has no y component. So the x component, Vx, is our resultant. As it falls down, the resultant velocity starts to angle downwards, and then eventually our resultant velocity is equal to the same magnitude, but at a different direction. So what do the graphs of this look like? Well, the horizontal position graph is going to not change. Well, the position changes, but the velocity is constant. So if the velocity is constant, the position is going to increase at a constant rate. So what does that mean in terms of the velocity? Well, we're going to go over this in detail, but for right now, the position versus time graph, the slope is the velocity. So we have dx dt, that is our instantaneous velocity. And because this slope is constant, our velocity is constant. Then, looking at the acceleration, the slope of a velocity time graph is our acceleration. And what's the slope of this line? The slope of this line is 0, so the acceleration is 0. If we work this backwards, the integral, or area under our graph, is equal to the change in velocity. So the integral of acceleration is our change in velocity. There is no area under this, so the velocity doesn't change. It's constant. And if we look at the area under a velocity time graph, that area is going to be equal to the displacement, or the change in position. So the area here is going to be the change in x. One more time, because this is so important, the slope of a position time graph gives us velocity. The slope of a velocity time graph gives us acceleration. The area under the curve or graph of an acceleration time graph gives us the change in velocity. And the integral of velocity, the area under a velocity time graph, gives us position. Now, the vertical component is much more difficult. The graph ends up looking like this. And let's look at y. Well, when it starts out, it has an initial velocity of some value up and positive. Well, we know that the slope of a velocity time graph is the velocity. So the slope is large and positive. But as time goes on, the slope decreases until eventually the slope becomes 0. So in the vertical direction, the slope is decreasing until it reaches 0. That's telling us about the y component. The y component decreases until it reaches 0. Then what happens? Well, the slope starts to increase. And as it increases, it's increasing in the negative direction, meaning it's speeding up, negative, which is down in this case, in the downward direction. So what does that look like on a velocity time graph? Well, it started out up and positive and decreased at a constant rate. Every second that went by, it decreased its velocity by 9.8 meters per second until it gets to the top. At the top, its vertical velocity is 0. It has no y velocity. Then the y velocity starts to increase. But what direction does it increase? It increases in the negative direction. So, what is the slope of a velocity time graph? Before we said the slope of a velocity time graph is acceleration. What's the slope of this line? It's constant and it's negative. So the acceleration is constant and negative. And we know on Earth that slope is exactly 9.8 meters per second squared, down, in our case, negative. If we do this in reverse, the area under this graph will equal our change in velocity, and the area under this graph will be equal to our displacement. In this case, we have positive displacement and negative displacement. These two cancel each other out. So where does the ball end? It ends at the same position it started at. This may look very confusing. However, stay with me on this, and this is the crucial part you need to understand to really get the idea of graphs. Let's say we have a position time graph that looks like this. The slope of a position time graph tells us the velocity at an instant. So this graph is curving, and the slope of this line at this point is this line. Well, that's the derivative of position with respect to time. So the slope of that line is the instantaneous velocity. The instantaneous velocity is right here. So the slope of that line right there tells us about the velocity right there. Well, what is the slope of a velocity time graph? The slope of a velocity time graph is the instantaneous acceleration. It's dv divided by dt. And that gives us the instantaneous acceleration. In this case, it's negative down here. But this value is constant because the slope is constant, so it's the same value everywhere on this graph. One more time, the slope of a position time graph tells us velocity. The slope of a velocity time graph tells us acceleration. Working in reverse, the area under an acceleration time graph is the change in velocity. The area is the change in velocity. That is to say, the change in velocity is the integral of acceleration with respect to time. So this area right here tells us about the change in velocity. Then, if we look at the area under a velocity time graph, that is going to be equal to the displacement. Or we could say it's the integral of velocity with respect to time. So, here it is, delta x, integral of velocity versus time. That's going to be whatever interval we choose from final and initial. So, recapping, the slope of a position time graph is instantaneous velocity, dx over dt. Slope of a velocity time graph is instantaneous acceleration, which is dv over dt, or the second derivative of position with respect to time. The area of under a under an acceleration time graph tells us the change in velocity. So the change in velocity is the acceleration, integral of acceleration with respect to time. These bounds are what we choose them to be. So for example, on an acceleration time graph, if we chose from t1 to t2, our integral would be t1 to t2 here. The area of a velocity time graph is our displacement. So displacement is the integral of velocity with respect to time. And again, the bounds are the time range. Our time range is from here to here. So that is going to give us our change in displacement over here. Let's look at an example of this in practice. So we're going to look at a function that defines what the acceleration is at any time t. But to make it simple, we're going to say that the initial position of this object is 0. It starts at 0 meters, and it also starts at rest. The reason that we're doing this is so that we don't have to worry about the constant plus c during our integration. When we integrate, the plus c will be 0. So let's look at what this is saying. It's saying that the acceleration at time 0 is 20. That means it's 20 meters per second squared, or every second it increases its speed by 20 meters per second. But as each second goes on, the rate at which it's speeding up is decreasing. This does not mean that it's slowing down. This means that it's speeding up at a slower rate. So eventually it's going to stop speeding up. And when is that going to happen? It's going to stop speeding up when the acceleration is 0. Well, let's throw in a 0 acceleration and solve for time. At 0 meters per second squared, it's going to be at 20 seconds. So, how can we figure out what the velocity is going to look like? Well, we know that the integral of acceleration tells us about the velocity. So, we have our change in velocity is the integral of acceleration with respect to time. And we're going to do this for 0 to 20 seconds. And we're going to put in our equation for acceleration, 20 minus t with respect to time. So we integrate. The integral of 20 with respect to time is 20t. And here we add 1 and divide by the new exponent, so that's 1/2 t squared. So I put in 0 and 20 in for our times to find the change in velocity, and that change in velocity is 200 meters per second. Well, you can do this in your graphing calculator if you want to, and you'll see that the line will start to decrease in slope up to here. So, what is the slope of this line at any moment in time? Well, the slope of a velocity time graph is our acceleration. So when we start out here, the slope of the velocity time graph is 20 meters per second. And every second that goes by, the slope decreases until the top, where the slope becomes 0. What happens? At 20 seconds, the acceleration is 0, so the slope of a velocity time graph is 0. Let's look at position. We know that position is the integral of velocity with respect to time. So let's take our velocity equation and integrate. So we have 20t minus 1/2 t squared. Add 1, divide by the new exponent, 10t squared. Add 1, divide by the new exponent, and we have minus 1/6 t cubed. If you throw in the numbers 0 and 20, that will give you a displacement of 2,666.7 meters. So, what does that look like? Well, on this graph, it's going to start out with a slope of 0, meaning that its initial velocity is 0. And as time goes on, the line gets steeper. What does that tell us is happening? It tells us that the velocity is increasing. And that makes sense because this is what it's doing here. It's increasing. But the rate at which it's increasing is decreasing. So let's go back and just look for a second at the integrals. So the integrals in each of these cases, the integral of the area, we did that. And the integral of the area is 200 meters per second. So that means we're going to see a change in velocity of 200 meters per second. And if we integrate velocity with respect to time, down here, then we're going to find that the area of this velocity is going to be 2,666.7. So, one last time, I know I keep repeating this, but it's so important to understand that the area of this is our change in velocity. The area of this is our change in displacement. And the slope of this is the instantaneous velocity, in this case, of this. And the slope of this is going to be our instantaneous acceleration here. In the next video, we're going to do a whole bunch of examples of this. And it's crucial to understand the examples to be able to do these problems confidently.